The previous session, we have spent some time understanding how to calculate torque about any point or any axis, and we have done some questions on equilibrium. In case of equilibrium, there is no angular acceleration, and we do some more questions on angular acceleration. And angular acceleration, if we take analogy compared to translation motion, it is equal to F is equal to ma kind of situation. See, if you have F is equal to ma here, and what are the other terms we have related to this? In case of linear motion, we write F is equal to something like a rate of change of F is equal to what? Rate of change of momentum also we write. And we write F into dt. What is that equal to? That's called impulse equal to change in velocity, change in momentum. Similar to this, we have similar equations in case of rotational motion also. Equivalent equation in case of rotational, in place of F, it is torque. In case of moment of inertia, it's a rotational moment of inertia. And this is F. So this is what is whenever torque acts on an object, when there's a net torque, it will lead to angular acceleration. And we can also understand after this, I will not doing it today, but I think we'll do in the next session is about, we'll do it tomorrow, is angular momentum. So if I write a similar equation, what is tau equal to? Rate of change of angular momentum. And similarly, we come across impulse. Impulse is, rather than having impulse, we'll have angular impulse. What is angular impulse? Angular impulse is equal to change in angular momentum. So these are the parts we are going to deal with the next session, that is tomorrow. So this is what we want to understand today. And that's the aim of this session. So let's see. And what is important here, the moment we come to topic of rotational motion, unlike linear motion, we have always keep in mind these equations are, see, torque also depends on an axis, I also depends on axis. And alpha actually, rigid body, alpha is constant, doesn't depend on axis, but these two depend on axis. So simple cases of angular acceleration. What are simple cases? The figure what you see is an example of simple case where motion is happening. If I call this an XY plane, motion is happening in the plane of the figure here. And in that case, axis about which rotation is taking place is perpendicular to the figure, which is a simpler example of motion. In this case, what is the motion? You can visualize this vertical wall here. And the rod is kept tied to a string here, and it is in a state of equilibrium initially. In equilibrium, it makes an angle theta with the vertical, and entire thing lies in one vertical plane. So it is not inclined or something. You can visualize it is in a one vertical plane. As soon as, and this is an equilibrium because what is that? The two forces are keeping in equilibrium. There's a force acting here, the tension is acting, and both of them are creating equal and opposite torque about point A. Moment we cut this string here, or any other way we put a supported, moment this rod is released from state of rest, it will have angular acceleration. As soon as the string is cut, uniform rod will have angular acceleration, and let's find its value. So when we have angular acceleration, this comes into the case of what you may call as a pure rotation, unlike rolling. In this case, pure rotation, this is something all particles are undergoing rotation about an axis, and axis is not in motion. Axis is in the state of rest. Pure rotation about an axis which is at rest. So it is about an axis. Can we easily identify this axis of rotation here? So whenever we use this equation here, we typically use it for about axis of rotation. In this case, where the axis, of course, very clearly, the axis is the axis of rotation, whichever point is on the axis of rotation, that point will remain at rest. So this is the axis which is rotation, and axis is perpendicular to the plane of figure. So if this whole arrangement is in vertical plane, axis is in horizontal plane. Okay, so that's what we need to keep in mind. So when we apply the equation, all terms should be with respect to fixed axis of rotation. In this case, this axis rotation is about a hinge, and axis perpendicular plane of figure and passing through A. So that's the thing I mentioned you need to visualize. And so when we calculate torque and I, both are related to that axis. Let's do that. To calculate torque, again we try either in the frame figure we can mark what forces are acting. Forces acting are like this. Moment that is gone, gravitational force will act at the center of mass. And hinge, as we mentioned earlier also, hinge can apply both component of forces. The hinge will have some reaction which has vertical component. It will also have reaction which has horizontal component. So what we need to find, and it's going to rotate about this axis. So we'll calculate torque also about A. and moment of inertia also is A. So what is talk about A here is pretty simple. Three forces are acting, and when we talk about A, two of them have zero torque. Because those two forces are passing through this axis here. So only one force, gravity, has non-zero torque and is vertical. Since it is vertical, its perpendicular distance has to be measured along horizontal direction. So this is angle, and if this angle is theta, it becomes equal to L by 2 sine theta. So torque is mg into L by 2 sine theta. And that has to be equal to moment of inertia into alpha. What is moment of inertia? So some of you may think, no, this rod is making angle. Axis is not here. It is not rotating. It will rotate. In that case, it would have traced out a cone. It is rotating about a horizontal axis. And since the rod lies in vertical plane, axis is the horizontal plane, at any point of time, you can visualize the rod will always make 90-degree angle with the axis. Axis is horizontal, and motion of the rod is taking place in the vertical plane. Angle between rod and axis is 90 degree. So axis is perpendicular to the rod about the end point. So what is moment of inertia of a rod about its end point? We can parallel axis now. Otherwise, also we can easily remember that is ml square by 3. So from here, I get an equation. So this value of, we arrive at value of alpha. And as we look at this expression, what we find here, this is proportional to sine theta. So as it keeps rotating, what will happen? This shape will shift. A moment start having angular acceleration. And we can also find out, sometimes they ask what is the, suppose the question asks, what is the linear acceleration of center mass at that distance? So linear acceleration of center mass r into alpha. So that will be L by 2 into alpha would be the linear instantaneous acceleration, tangential acceleration at this distance. And since when it just started rotation, its angular velocity is 0, it will not have its centripetal acceleration as soon as it is released. Now coming to other part here, as the theta, let's see, basically it will, after some time I'll find it has come to, it will undergo angular displacement also. And as it keeps falling, what we notice, angular acceleration is not constant. It increases with theta, because sine theta increases up to 90 degree. So angular acceleration will become maximum when theta becomes 90. When it comes to horizontal position, that's the time it will have maximum angular acceleration. Afterwards, again, angular acceleration in terms of magnitude will start decreasing. So that is something, all the things we need to understand here and keep in mind. And when it becomes horizontal, it is 3g by 2l. It is 3g by 12 means what would be the acceleration of this point here? So when it becomes horizontal, acceleration is 3g by 12. It means instantaneous linear acceleration of this point here is 3g by 2. So this point on the rod is moving downwards with the acceleration greater than d. So if I have another mass which is falling, compared to this mass, this will have faster acceleration. And this because of rotation is happening. Okay, so that's the point we need to keep in mind. And let's look at some more example of the same. Another thing you can think of is we will continue with some more example of rod. Suppose we have again you have a thin rod, and we know if we thin rod, if we keep a pivot at the center, it will be in the state of what you may call as unstable equilibrium. Any small displacement will start rotating. So if it is hinged about midpoint, it will have unstable equilibrium, unstable rotational equilibrium. Any other point, it will not be in a state of equilibrium. Suppose I hinge it about a point which is at a distance L by 3 from one end. And from it is in the horizontal state, if I release it, if from horizontal state, what would be the angular acceleration? So again, let's examine here. Let's mark what the forces are going to act here. Again, if I mark all the forces here, the forces could be the forces. Hinge can apply forces in both components it can have. So it will have hinge may have reaction, vertical component. It may have also horizontal component. And as soon as I release from here, this is empty. Okay, so when and it is acting at central mass. So can we calculate here? Do we easily identify axis of rotation? In this case also, axis of rotation is perpendicular to the plane of figure. It's a horizontal axis, and since the rod when it rotates always in the vertical plane, angle between axis and the rod will always be 90 degrees. So, okay, so let's look at what the torque will be. The moment of inertia about axis of rotation. I can see from here it is L by 3, this is L by 6. So I can calculate moment of inertia About an axis perpendicular to rod, I can apply parallel axis theorem. About center of mass, it is ml square by 12 plus m into L by 6 whole square. That is my parallel axis theorem. I obtain moment of inertia about axis of rotation, and will calculate torque also about axis of rotation, which is mg into L by 6. Which direction torque is acting? Same direction alpha also will act, and little time later, if this is the direction of alpha, value of angular velocity acquired also will be in the same direction here. Okay. So that's let's equate. So three forces acting, only mg will have non-zero torque about A. Mg into L by 6 is equal to moment of inertia about axis of rotation into alpha. Okay, so we can calculate that one. Let me ask one more thing here. See, when this instance, if I ask some of you, can someone guess what would be at this particular instance? Is it possible to calculate RV and RH here? How do we calculate vertical component of reaction acting in the hinge and horizontal component of reaction acting in the hinge? So horizontal component is fairly easy. There are two ways we can understand why horizontal component is zero. Well, what are ways we can think of horizontal reaction? For horizontal reaction, we can think of motion of center of mass. If I this is the object here, if I take this center of mass here, and at this particular instance, the center of mass has zero acceleration in the radial direction. Soon after release, its velocity, angular velocity is zero, linear velocity is zero, centripetal acceleration is zero. It only has tangential acceleration. Since centripetal acceleration is zero, net force acting on the center of mass, net external force in horizontal direction has to be zero. And only external force, three external force acting. If net horizontal force is zero, it means at this particular instance, horizontal component of force exerted by the hinge will be zero. And since it has a downward acceleration, if I look at this, actually it is as a downward acceleration. Soon after it is released, RV will be less than mg. You can calculate that also, but I think this get an understanding of motion of center of mass. Okay, these are some simple questions which have come in the past also. A similar variation of previous questions. All of you just read that question and try to think in your mind. Let's just read out of the question. It's a massless rod of length 3L. It has two masses attached at each end as shown. So here also mass 5m attached. And rod here other m, 2m is attached. And it is pivoted about point P, point P on the horizontal axis. Okay, so axis of rotation, again it can rotate in vertical plane. Axis of rotation here also is horizontal. So when released from initial horizontal position, what is instantaneous angular acceleration? Okay, so this is a figure given, and a very similar figure had come in the main sum. So let's see which are the areas where you might get confused and how to avoid such confusion. See, two masses are shown here, but two masses, though figure is shown like a ring or whatever, but nothing else is mentioned about shape and size. Whenever shape and size, nothing is mentioned, we have to assume the radius is so small, we can treat both objects like a point mass. So both objects, no radius and all, we don't have to worry. This is something which is like a small ring, it's like a point mass. So entire thing can be viewed as 2 point masses placed on a massless rod. If I have to visualize a equivalent figure here, if this is the rod, which is a massless rod kept here, which are the weights here, this is the mass here, and this is mass here. That's all. Here you use 2 point masses. And here this is reason you have to understand why is it so. So sometimes question information something is missing and you need to understand what it implies here. Easily identifiable axis of rotation and hence torque and moment of inertia has to be calculated about point. So how's the axis here? Axis here is again either plus k cap and minus k cap if this is xy direction. So if we calculate torque here, it should be fairly easy to calculate here. Again, we'll draw a diagram. All of you try the diagram. What are the forces I can identify? Where is the axis? How will calculate torque and how will calculate moment of inertia? So you can do that. I'll look very simple here. So if I mark here, the torque will be equal to this force will be 5 mg will be acting. So I notice there are two torques here, 5 mg and at a distance L. So this will create a torque which will tend to go in an anti-clockwise direction. If I draw both torques here, 5 mg is the force, vertical direction, multiplied by horizontal distance L, which is in direction anti-clockwise positive. And this also created torque that will equal to minus because it is in the clockwise sense. And force is equal to 2 mg. Length is equal to 2L. So I find net torque comes equal to mg. And what is moment of inertia? How do we calculate moment of inertia here? Rod has no mass, so no ml square and not, only 2 point masses. And from this axis, the point mass, it is mass into square of the distance, so 5m into L square, plus 4m into L square. So that comes equal to 13 ml square. That's the moment of inertia. And alpha is easy to obtain. So this was a question. It's a very, very easy question. So those who have basic understanding of rotation motion can easily solve this question. No complication here. Can be done in about a minute's time or even less. That's a little tricky question, not a mains question. So basically slightly more than most questions which have come. Let's try to identify, understand here. Just first understand what the figure is. A rigid body is made of 3 identical thin rods. You can imagine you can get 3 pieces of rod and you can form an edge. All 3 identical, all lengths are same, masses are same. Each of length L fastened together and form a little edge. The body is free to rotate about horizontal axis that runs along the length of the one of the leg of the edge. How is the axis? Edge, this axis of rotation, and this is horizontal. This is something is given, it's a horizontal axis. So though figure is given, you need to visualize how the rotation will take place. Now this slightly 3 dimensions are involved. The body is allowed to fall from rest from a position in which the plane of edge is horizontal. The entire thing is in horizontal plane. I release it from there. What is the initial angular acceleration? So this axis is okay. Similar places that the way we calculate torque. So I need to calculate torque as well as moment of inertia about this axis which is shown here. And alpha also be about this axis. Let's try and think here. So whenever you have such question, previous question, figure was drawn with axis perpendicular to the plane of figure. So what is the viewpoint? Suppose you stand here and you observe the figure. What would this axis look like if you stand along the axis? Axis will look like a point similar to previous one. And this entire rod will look like a point. This rod will look like a horizontal length, and this rod also look like a point. If you look from along the axis from a distance, and second thing what we notice here, see in this case to calculate moment of inertia, this entire rod will not have any moment of inertia because the entire piece, this entire mass, I can replace with the point mass because the length is not changing. And similarly, this entire rod is at a constant distance from axis of rotation. So this mass also for calculation of moment of inertia can be replaced with the point mass. So this is something I think those who have paid attention yesterday will understand a little better. Let's view from the axis. How would the figure look like? This is how the figure. This rod will look like this. This is the cross section of the rod. This is the rod B here, what we see here, and this is the rod C here. So mass M for mid piece, piece B is this, A is this, and C is this. And entire mass is at the constant distance from axis of rotation. So if we understand this figure, let's all is really simple here. Let's do what is the torque which will act. So this torque weight will act along this direction. So forces are this direction plus reaction here plus weight of the rod acting at the central mass and that's it. So if I calculate torque here, how many forces? Forget reaction and forget this weight. Only these two will have non-zero torque. And this will act at a distance, total length of the rod is L, so this will be L by 2. So it will be equal to mg into L by 2. The torque due to weight of B and torque due to weight of C will be equal to mg into L. And you understand here, if I imagine this rod to be composed of small pieces, all pieces wherever weight is acting is distance from axis is constant. All are in distance of L from the axis. 3 mg per L by 2, that becomes my torque here. And what is moment of inertia? This axis and its axis is perpendicular to plane of figure. So it is and this piece end of the rod perpendicular to rod. So it will be equal to ml square by 3. And this is like a point mass. All mass is equidistant. If you imagine, otherwise also you want to understand, if I take a small pass here dm, what is the distance of dm from here? The distance of dm is L. And all small pieces are at the same distance. So if I add up moment of integration, it will be equal to dm. into L square, and if we add for all this thing, it becomes equal to ml square for rod C. So rod C, ml square. So this is the moment of inertia. And once I have moment of inertia, I can easy for torque by moment of inertia is equal to angular acceleration. Right. Next one, let's say two equal and opposite forces, each of magnitude f, act on a smooth rod. So you can imagine on a smooth surface, if you have a very smooth surface like a granite tabletop, and you have a metal rod here, steel rod, you place it like this. You can also maybe possibly can tie string, and string makes a 30-degree angle. And if you apply equal forces along the string at an angle 30 degrees with the length of the rod, what kind of motion the rod will have? And you see, suppose this whatever force you apply, it is connected through some kind of measure with gauge which shows what the force is applied here. So can we find out what kind of motion it will have? All parameters we can find. First of all, if this object mass is m and length is l, what torque will act? Now, unlike previous cases here, in all previous cases we have defined there was fixed axis it was rotating about. So when I'm asking torque here, we have about which axis? Axis is not defined here. What is net torque here? But even though axis is not defined, still we can find a torque because of spatial region. What is the spatial region? Is forming equal and opposite forces. And whenever equal and opposite forces are there, they are called a couple. And couple creates a torque, and magnitude of torque is independent of choice of axis. Any axis we calculate, it will come out to be same. And we have discussed this one in the second year of the topics. So I can take this force as two components. One way I can think of, we can have two components here. One component along the length of the rod, and we can have another component which is perpendicular to the rod. And once you mark those forces, what we notice is the length component which is along the length of the rod will not create any torque, whereas the components which are perpendicular will create a torque here. And what would this perpendicular component will be? Along the component f cos 30, this will be equal to f sin 30. Both are f sin 30, f sin 30, and it creates a couple. And what is couple equal to? A couple is equal to force multiplied by perpendicular distance between the two. I could have also done other way without taking component also. This is a couple here. I can extend the line of the force. And if from here, at this point, if I drop a perpendicular, the length of the perpendicular is equal to perpendicular distance, which also again gives me the same value. So which distance? This is my perpendicular distance here. So again comes equal to L sin 30, F into L sin 30. Whichever way, both ways you can understand here. So what is net torque here? Net torque is easy. This is what net torque we calculate, F into sin 30 into L, which equals equal to FL by 2. And second thing, what you notice, whenever couple acts, net force is 0. So when I look at this net force is 0, is center of mass which is here, even if you apply this force afterwards, the rod will rotate, but its center of mass will not change, which I mentioned earlier. Also, the center of mass will remain the same. So even though it is not fixed, this rod will move as if it is fixed about center of mass. So center of mass will behave like a fixed axis of rotation. So even if this was pinned and fixed about vertical axis, its motion would have same. It will behave like a fixed axis of rotation. So what is angular acceleration? This is axis of rotation. So this is the torque which is acting. Moment of inertia about axis of rotation which is passing through center of mass is ml square by 12. So I get angular acceleration. Acceleration of center mass is 0. And here important point is net torque does not depend on the frame of reference because it is forming a couple. That's the point. Example of couple equal and opposite forces. Net force is 0. And net force is 0. That's why center mass will remain unchanged, remain stationary. And if it is stationary, it's like a fixed point. So not rod will have pure rotation about center mass. So this example of without having fixed axis of rotation, this particular point which acts as a fixed axis of rotation. Other examples, let's take this kind of question also have come in the past, and but they're important ones. Let's understand these questions as well. So in this case, you have some of you might have seen a pulley kind of thing, which some pulley can be used to draw water from the well and other things. So this string mass m is supported. A string is wound around a uniform cylinder. You take a cylinder round this one. So basically, to wind it, you can also have a fixed point. So you tie one end the rod on some point on the pulley, and then you run it around. And then you take it down, and mass is hanging from here. Right. So cylinder is the mass of the cylinder. R is the radius. We assume it is a uniform cylinder. And if it is we hold it like this, it is released from the state of rest. When it is released from rest, what will happen? This also will start having angular acceleration, and this block will have downward acceleration, linear acceleration. There's alpha term here related to rotation of the cylinder. There's a linear acceleration related to linear acceleration of mass. Okay, and in such case, when the string is wound here, there's one very, when the string is wound, very easily we should understand here. So when the string is wound, no slipping is taking place. So we can take 2 points. What are the 2 points which are in contact? I have taken one point which is on the cylinder in contact with the string here. So there are 2 points. One is the string, another is part of the cylinder. And there will not be any slipping between them. So there is no slipping. So this point has an acceleration of A here, which is on the string. This string, every part of the string which is tangential to the drum will have same motion as block M. This has acceleration A. Whereas another point which is negligible distance apart, which is on the cylinder, it will have angular acceleration alpha. Angular acceleration instantaneous, it will have a linear acceleration of R. So this point on the drum has a linear acceleration of R alpha. Point on the string has an acceleration of A. Both have to be equal. So this is based on A and alpha are related. A is equal to R alpha. This is based on no slipping happening at the point of tangency or later on. So this let's apply this condition here. So how do we solve that question? We'll use this condition. We'll take 2 cases because we cannot combine rotation and translation. These two are having different type of motion. We'll take this object separately and we'll take this system separately. For this system, we'll calculate alpha. This system will calculate A. And moment we take as a separate system, there's a contact force here. We replace contact force with tension here, force here. And it will have T here. And of course, it has some force acting here also. And this support here, this is something T dash. When I look at this object here, let's analyze this object will undergo rotation. About which axis? This axis of rotation. So to calculate this alpha, I'll calculate torque here. What is the torque created here? Is weight will act about the axis. The reaction also will act about the axis. This weight and axis will not create any weight, and this force will not create any torque. So torque is only due to tension here. So this cylinder, if I analyze cylinder here, let's look at this how we calculate cylinder. So from free body diagram of the cylinder, alpha will be equal to torque about axis of rotation divided I about axis of rotation. Torque will be equal to T into R. And what will be moment of inertia about the axis of a cylinder? Axis of cylinder moment of inertia is mr square by 2. That's alpha here. You can easily calculate. And how about this object? We know that T is equal to what? When it's an upward acceleration, mg plus A. It is downward acceleration, g minus A. Or we can actually calculate A. A will be equal to mg minus T by 2. And these are two very easily can arrive at. So point I'm making here, two things. We analyze this separately. We analyze this separately. But these two quantities are related by this relation. If we apply those things after calculating, arriving at alpha and A separately, we will substitute into this, we get our answer. So no slipping, point in contact with the point on the rope will have same velocity and acceleration. R alpha is equal to A. And angular acceleration of cylinder, we arrive at, that comes to this. And we can arrive at acceleration of the block also, mg minus T by n. Based on this, I calculate value of alpha. From these two equations, two unknowns, and we can arrive at alpha also, we can arrive at A. And when you arrive at alpha here, so this alpha A is nothing but R alpha. So if it is R alpha, I have written in this particular form. I could have cancelled R and I have not cancelled for the particular reason I have not cancelled. Because the reason I have not cancelled is, okay, so what is the term we see in the denominator? if I divide this denominator term also by r square, so when I write a value we actually multiply by r, and if I divide numerator and denominator by r square, I get this expression mg divided by n plus I by r square. This expression I get, and see, this is something, let me try and understand. This is something, let me see. Can I understand this expression is slightly different way? So in this case, if I compare with something like Atwood machine, if I compare with Atwood machine here, what happens in case of Atwood machine? This is something, if we have a pulley here. In Atwood machine, something with two masses are suspended, M1 and M2. If this mass is heavier here, if this mass is M2 and this is M1. How do you used to write the expression here? Expression was M2 minus M1 divided by M1 plus M2 into G. That was the expression. So something similar to this also. Let's see what happened here. This is gone here. And, just 1 minute. Interpret, because there's another way, but basically it's like a shortcut kind of thing. But let's say I understand and we get some reason also why this. So let me look at what does this expression mean here. This expression, if I think of it, but this what is expression I'm getting here. See here I get two equations, and when I eliminate t, I get a relationship between, if I eliminate t, I get the value of alpha. And when I eliminate t, this expression becomes something like this. If I remove t part here, this basically, if this string is gone, then this mass m is something like fixed on the perimeter of a cylinder here. So if I replace this system with the point mass, which is I shift this mass here and remove the string here, what is the torque acting on the system? Torque acting on the system is energy. And what is the moment of inertia of the system here? Moment of inertia is moment of inertia of the cylinder plus moment of inertia of this mass here. What is angular acceleration? Our angular acceleration is mg into r divided by what? Divided by total moment of inertia. Moment of inertia of the cylinder plus the moment of inertia m into r square. So if I divide whole thing by r square, I get the alpha. So you understand, this is something we can think of something like this also. And reason also simple, and that is only true for instantaneous case. Instantaneous case, this is how it will happen. And because string anyway, it gets eliminated, same tension is acting on both. And I can use it some of other example. Let's see how do we use the next case. So suppose we have question like this. This extension of the same, and one important point what you have to keep in mind. In this case also, there's something of pulley arrangement. Unlike previous case, the string is not wound around it. The string goes like this. And those who have seen a kind of pulley may have some kind of gear also. It may have something like this. So basically, or it has to have rough. So whenever I have such question, it is a case where the surface, this pulley is not a smooth. So either have a gear or something, so there's no slipping. And no slipping is possible only if this pulley is rough, or it has some kind of this kind of teeth which doesn't allow rope to slip. So it's shown moment of inertia. So this is the pulley here. Unlike previous case, the string is run around the pulley. It's a rough pulley. The string is light and does not slip on the pulley. Now we have two masses. This mass is heavy, this mass is light. If this was smooth, what would happen? Both side tension would be same. But because of force acting in between, it just is something, because here the friction force also is acting along the length of the string, it has a tangential component. So tension here is important point, T1 here and T2 will not be same. T1 and T2 will not be same. And you can imagine that way also, but this something, see, if you have a string, suppose there's a rope here, you can think why it is not same. Suppose there's a rope here. If a rope weight M is suspended here, okay. So in this case, if there's a thin rope here, everywhere tension will be empty. But if a person is hanging onto the rope, what will happen? The person, if he is hanging onto the rope, he will curl his hand around the rope, he will press the rope hard, and pressing the rope hard will give you normal reaction. But because of normal reaction, friction force also start acting. So moment there's a friction force acting, and friction force on the rope is acting in the downward direction. So what will happen? The tension on this side and tension on this side will not be equal. So something similar. So moment friction acts, which has component along the rope, the tension on both sides are not equal. So these two tensions will be unequal. So if I have to solve this question, how do I solve in a slightly longer method? If this is acceleration A, this will move with an acceleration A. Length of the string is not changing, and this will have alpha. So what in my equation is R alpha is equal to A and A. I'll calculate this as one system. I'll calculate A for this system, T1. I'll calculate for this system, so I can eliminate T1, T2, and I can solve, which is a lengthy way to solve. And mains question that becomes a little too long. Okay. So how else I can solve this question? And when the tension of the steel train will not be equal, and you understand why it is not equal, because there is a force acting which has component along the length of the string. So if I take free body diagram of the string, most cases used to take the free body diagram like this, T and T. But somewhere along the string here also some force is acting, then these two tensions cannot be. Net force in any small part of the string has to be zero. So if I take a small piece of the string, here tension is T, and in between, because of friction, some force F1 is also acting. The tension other end becomes equal to E plus F1. So net force on the small piece of string has to be zero. So something like this is happening. The friction must be present. Then only it will happen. I can replace, if I go by the old logic, I can replace this mass here. Okay, this mass is more like attached here. Remove this string, attach this mass here, and remove this mass here, attach it here. If the system becomes like this, let me see what is the alpha of the system. This mass is heavier. It will tend to rotate in this direction. Let me write alpha now because of pure rotation question. And pure rotation question, let me easily write what is torque here in this case. Now, what are forces acting? Force will act at the support reaction here. That will, and weight of the pulley will act. Both will act along the axis of rotation. So this will not create any torque. But torque is created only by due to this force, capital Mg and small mg. And both torques are in the opposite direction. So net force becomes equal to capital M minus small m into G. So that's how we'll solve, and that is perhaps much, if you understand that logic, it's much faster way. Angular acceleration, first I calculate torque here, minus m. What is the torque here? Torque is equal to m minus small m g into r. And what is the moment of inertia? Moment of inertia is the moment of inertia of the cylindrical drum plus moment of inertia of this mass, which will go to m into r square plus small m into r. That's the equation. Okay, I think R term have missed. This R term also will come. Okay, so that's the expression. I hope all have understood. This another we can solve. And this kind of questions are important and common. Okay, so that's all we need up to this point. You need to understand. So that are the questions on acceleration. Acceleration, rotation about fixed axis of rotation. I'll stop here for today, and from